So in this section we'll look at polynomial models and functions. So let's just start off with their definition. So the definition looks kind of complicated, but when you look at some concrete examples, they're usually easy to identify. So let's go through the definition, then we'll look at some examples. So a polynomial function is one that has the form f of x equals a sub n times x to the n plus a sub n minus 1, x to the n minus 1, and a bunch of other terms with a possible linear term and a constant term, where x is the independent variable and is a non-negative integer, and the a's are all real numbers. You can study them in the context of being complex numbers, but in this course we're just going to be looking at real numbers, real valued functions. So there's a few things here in terms of terminology. So the largest power, which here is going to be n, this is known as the degree of the polynomial. A sub n is known as the leading coefficient, and a sub 0 is the constant term. And as we said, a0 is the constant term. So these are all things that I'll say quite regularly in terms of identifying the different coefficients of interest with regard to the polynomial. So the first thing we'll want to look at is some examples that show what polynomials look like and some examples where perhaps they fail. So we'll say, is the given polynomial, or is the given function a polynomial? And if so, polynomial, and then if so, identify the degree. So this first one, we have f of x is equal to 14x to the third power minus 3x plus pi. So for each one of these you may want to pause, think about it in terms of the definition we just wrote down, and try and hazard a guess. But this one, the answer is yes. And the degree, the highest power of x that we see, is equal to 3. So you really want to think about what could go wrong in terms of something being a polynomial. Coefficients being real numbers, we're probably not going to encounter too many complex numbers, so that's usually not going to fail. So the real kind of linchpin is the part that concerns the degree, because the degree has to be a non-negative integer, that n value, and then every single one from there is just subtracting a integer. So basically all the powers of x's that we see are going to have to be so you're going to have your constant term, and then all the powers of x that actually appear are going to be positive whole numbers. So if one of those fails, then that's when we're going to see the term not being a polynomial. So let's look at the second one, g of x. Let's say that's 5x to the 7th minus 13x plus 8 divided by x. So think about this. Do you think g of x is a polynomial? All right, so the answer here is no. Why is the answer no? Well, it's because 8 over x, if we wrote it in terms of the exponent of x, it would be 8 times x to the negative first power, and negative powers of x are not allowed. So one more example, but you kind of get the idea here. So let's say h of x equals 10. So what do you think? Is this a polynomial? Is it not a polynomial? The answer here is actually yes. So then the question is, what is the degree, since we don't see an x appear anywhere? Well, remember, x to the 0 power would be equal to 1. So we could think about this as like 10x to the 0. So for that reason, we say the degree is equal to 0. All right, so moving forward, I actually have one more example for us to look at. So, there's other kinds of functions. Again, notice the variable was always just in the base, so it can't appear in the exponent. So another example of something going wrong. And there's lots of different things that would cause it to fail, so we're just looking at a few typical examples, but say 5 to the 2x plus 1. So this is no. A variable in the exponent is not allowed either. So we looked at linear functions already. All linear functions are examples of polynomial functions as well. So now we'll move into another specific subset of polynomial functions, namely the quadratic functions. So the quadratic functions are ones that we understand very well. And so let's look at the quadratic functions. So the quadratic functions are just the polynomial functions where the degree is equal to 2. So these are polynomial functions with degree equal to 2. So, specifically, if we want to write down a general form, so a general form here would look something like f of x equals ax squared plus bx plus c, where a, b, and c are just real numbers again. So one thing that we want to think about in terms of the quadratic functions is we understand, can we solve the quadratic equations that result from, say, letting f of x equal some number, and also, can we sketch their graph quickly? So let's answer the second of those two questions first, finding their graph. So the easiest way to find their graph is using a result known as the vertex formula. So the vertex formula, what does that state? So the vertex formula says the vertex of a parabola, which is the name for the graph of a quadratic function. So the vertex of a parabola occurs at, given the general form above, x equals minus b over 2a. So the y-coordinate still has to be determined, but basically what happens is you find the x-coordinate of the vertex and then just plug that into the formula for your function. It's not worth trying to get a formula for the y value and memorizing that when the formula for finding the x-coordinate is so simple. So let's go ahead and look at how we can graph one of these things. So in the example, we will say, sketch a graph of, let's say, y equals x squared minus 4x plus 2. So let's first find the vertex. So I'll break it down in two parts, finding the x-coordinate of the vertex. So the x-coordinate of the vertex, well, b is -4, so it's going to be -4 divided by 2, and then the coefficient of x squared is just 1. So this comes out to actually +2. So to find the y-coordinate, what we do is we plug that in, plug 2 in for x in the above formula. So y is going to be 2 squared minus 4 times 2 plus 2. So this looks like it comes out to, let's see, 6 minus 8, which is -2. So our vertex has coordinates 2, -2. Now the parabola, you can quickly tell whether it's going to open up or down by looking at the leading coefficient. So if the leading coefficient is positive, it'll open upward. If it's negative, it will open downward. So the easiest way to sketch this is to just first find that vertex, which we saw was at 2, -2. So this point right here is the vertex. So since the parabola opens upward, that's going to be the bottom point of this parabola. So we want to find at least 2 other points to get a rough sketch of the shape. So another point that we know that we can write down quite easily is the y-intercept. So if you plug in 0 for x, you get 2 for y, right? All the terms go away except for the constant term. So the y-intercept is going to be up here at 2. Now, parabolas have a very nice symmetry. If you draw the dotted line through the vertex, that's what's known as the axis of symmetry. So the parabola is going to look exactly the same to the left and to the right. It's going to be a mirror image on either side. So 2 steps left of this dotted line, we have a y value of 2, which means if you went 2 steps to the right of this dotted line, you would also have a y value of 2. So from there, that's enough points to give a rough sketch of the important features of our parabola, which is this kind of upward U shape through those 3 points. Again, for more specificity, you can sketch more points, but to just get a quick idea of the important features, the vertex and the y-intercept are typically good enough. Sometimes you have to use a different point if the vertex happens to also be on the y-axis, because then it will be your y-intercept. But usually that's just going to be some easy translation. Okay, so let's do one more of these. So example, let's sketch a graph of y equals -3x squared plus 6x minus 4. So same drill here. We first want to start by finding that x-coordinate of the vertex, which in this case is going to be -6 divided by 2 times -3. So we get +1 as the x-coordinate. So the y-coordinate is going to be y equals -3 times 1 squared plus 6 times 1 minus 4. So that comes out to -1. So our vertex here is 1, -1. And we see that the y-intercept is 0, -4. That's also quickly identified. So notice also that this parabola is going to be open downward because the leading coefficient is -3. So that -3 means it's going to open downward. So 1, -1, the vertex is right here, and 0, -4, the y-intercept is right here. Again, the axis of symmetry is going to be x equals 1. So essentially my other point has to be on this side of the dotted line. So there are your 3 points. And there's the graph of the parabola. So that's that. Okay, so now let's look at solving quadratic equations. There's going to be 3 different techniques that we look at. So we can graph these things. Now let's see about solving them. So the three techniques are going to be the square root principle, factoring, and quadratic formula. So let's break those down one by one. So the square root principle happens typically in a special case where you can just solve for x squared if there's no x term. In fact, it's more general than that. These techniques kind of all go hand in hand with one another. We use the idea of the square root principle and factoring to actually come up with the idea of the quadratic formula through the method of completing the square. But I don't think we're going to be going over that. We're just going to look at the specific techniques here, since we'll encounter them, and we want to get to the applications as soon as possible. So what is the square root principle? So let's start there. So the square root principle says that if k is a non-negative number, so let's say if k is greater than or equal to 0, and you have some expression a squared equal to k, then you can solve for a, and a is going to be plus or minus the square root of k. Pretty straightforward. So let's look at just a quick example there. So we just want to solve each equation. So a, let's see, x squared is equal to 361. Well, this is easy enough. We just write down the formula. So x is plus or minus the square root of this 361. And the square root of 361 is 19. So we have two answers there, x equals plus or minus 19. Both are solutions. Maybe slightly more complicated, but not really. Let's look at 9x squared equals 25. Kind of two ways to do it here. You could divide by 9 first, or you could realize that 9x squared is 3x times 3x. But if we divide by 9 first, we end up with x squared equals 25 over 9. So then x will be plus or minus the square root of 25 over 9, which simplifies to 5 over 3. So x is plus or minus the square root of 25 over 9, right? And 5 over 3 times 5 over 3 makes 25 over 9. So x is going to be plus or minus 5 over 3. So this is, when you see the square root principle as an option, typically it's going to be your fastest option to solve the equation, but you know. All right, let's look at maybe one more. This doesn't just have to be simple numbers. Sometimes you can use it with algebraic expressions. So imagine we just so happen to have the equation 5x plus 3 quantity squared equals 289. Well, we can use the the square root principle here because we have an entire expression squared. So we can say 5x plus 3 will have to be plus or minus the square root of 289. So 5x plus 3 is equal to plus or minus 17. And then what you want to do is you just want to separate this into two equations. So 5x plus 3 is equal to minus 17, or 5x plus 3 is equal to 17. And then you can solve each of those linear equations, so I'll leave the details to you. Basically, you're just subtracting 3 and dividing by 5, but the two resulting solutions should be x equals negative 4 or x equals 14 over 5. Again, I've skipped the steps there, but if you've watched the linear equations video, that should be pretty easy. Just subtract 3 in both equations and then divide by 5. Okay, so let's move on to the second technique, factoring. So again, we're trying to factor something of the form ax squared plus bx plus c equals 0 typically. So this factoring technique itself breaks down into two cases. So the cases depend upon the leading coefficient. So one, if the leading coefficient a is equal to 1, this is kind of your easy case. And if a is not equal to 1, that's your more difficult case. So I'll call it the hard case, but it's not. It's just 2 extra steps, essentially. And so the technique we'll be using to factor is known as factoring by grouping. So the easy case we'll just learn by doing some examples. So example, we will say solve by factoring. So a, let's suppose we have x squared minus 13x plus 42 equals 0. So what you have to do is you look at the constant term. So the constant term in this case is 42, and we just want two numbers that when you multiply them together, they multiply to positive 42, but when you add them together, you get that middle term, negative 13. So in this case, negative 6 and negative 7 do the job, and that just tells you the factors immediately. So x minus 6 times x minus 7. And you can check by foiling that this is actually the same as the expression above, right? X times x would be x squared. Your outside factors would be minus 7x, and your inside factor would be minus 6x, so those together add to negative 13, and then when you multiply them, negative 6 times negative 7 is positive 42. So that's why that works. And if you're solving this equation, when you have two numbers that multiply to 0, one of them has to be 0. So either x minus 6 is 0 or x minus 7 is 0. So we have x equals 6 or x equals 7. And those would be your two answers to that equation. Okay, so for B, let's look at x squared plus 21x minus 72 equals 0. So again, same deal. We're looking for two numbers that multiply to negative 72, but when you add them together, you get that middle number 21. So go ahead and pause your video and give yourself a second to try and figure out those two numbers. That's kind of the crux of this first technique, being able to do that. All right, well, if you had found 24 and negative 3, you got the correct answers. So basically this factors into x plus 24 times x minus 3 equals 0. And then solving each equation separately results in your two solutions of negative 24 or positive 3. So sorry, let me clean that up a little bit. So x equals minus 24 or x equals 3. So that is going to be that. All right, so let's move on to the second technique. The second technique is going to be the grouping method. So, example, so actually let's note that first. So this is 2 factoring a not equal to 1, and as stated before, this is known as the grouping method. So let's just jump right in with a couple of examples. It's going to be it's going to have a similar feel to the previous technique, but like I said, we're just going to have a couple of extra steps thrown in. So if you already know a different way on how to factor these and you're comfortable, that's fine. The grouping method, I think, is just the most commonly taught now. So let's look at 5x squared minus 22x minus 15 equals 0. So what you're going to do now is we multiply the first number, 5, the leading coefficient, with the constant term, negative 15. So if you do 5 times negative 15, we get negative 75. So now we're playing the same game with this number and with a negative 22 in the middle. We want two numbers that multiply to negative 75, but when you add them, you get positive 22. So the numbers that work here are negative 25 and positive 3. And basically what we're doing is negative 25x plus 3x makes negative 22x. So we're splitting apart that middle term so that we're going to have two pairs of terms. And we're going to take the greatest common factor out of each pair respectively. So we now can write this as 5x squared. And it doesn't matter which order you write them in. You could do plus 3x minus 25x instead, but I'm going to write minus 25x plus 3x minus 15. So then your pairs, you have this first pair of numbers, 5x squared minus 25x, then your second pair of terms, 3x minus 15. So you want to take the GCF out of each group. So the first group, they can both have a 5x in common. And then inside we'll have x minus 5. Again, you can check that you did it properly by distributing. 5x times x is 5x squared, and 5x times minus 5 is minus 25x. And then the second group, we can take out a 3. So if you take out the 3, notice you'll get actually the same matching factor. So that's the whole goal, because now the thing in parentheses actually turns into a common factor. So your final factored polynomial looks like the 5x that's in front here plus the 3 times your common parenthetical factor of x minus 5. And then you can break apart those factors to solve just as you did in the previous examples. So we have 5x plus 3 equals 0, or x minus 5 equals 0, and then if you solve each one, the first equation has solution negative 3/5, and the second has solution x equals 5. And that's that. So let's try another one. Let's look at 3x squared plus 17x plus 24 equals 0. So what do we do first? We multiply the 3 with the 24, so we get 72. And we want two numbers that multiply to 72 but add to 17. So this time 8 and 9 do the job. So we have 3x squared plus 8x plus 9x plus 24 equals 0. And we look for our factors. So what is the common factor of 3x squared and 8x? Well, they have no common numerical divisors, so the only thing we can take out there is an x, and we get 3x plus 8. And then from the second group, it looks like we can just take out a 3. So if you take out a 3, on the inside we also get 3x plus 8. So now you can see the two factors that we get. We get x plus 3 times 3x plus 8. And that equals 0. So we can separate that into the two linear terms that we need to solve. So either x plus 3 equals 0 or 3x plus 8 equals 0. So we have our two solutions, x equals minus 3 or x equals minus 8/3. So that's it for those two grouping. Let's do two more examples, then we'll move on to the last thing to complete the section, the quadratic formula, which really just amounts to plugging in some numbers. But anyway, 6x squared minus 13x minus 5 equals 0. So 6 times negative 5 is negative 30. And two numbers that multiply to your middle term of negative 13. So negative 15 and positive 2. Again, you got to be a little bit careful with your signs. Remember, we have one positive, one negative here. a lot of people might jump the gun and say, oh, -10, -3. So you have to be really careful. The problem with -10 and -3, they both add to -13, but they multiply to +30, not -30. So sometimes if you're going too quickly, you might get a negative incorrect like that. So then we split the middle term. So 6x squared minus 15x plus 2x minus 5 equals 0. So the first group we can take out a 3x, and we're left with 2x minus 5. And then we already have 2x minus 5, so in that case you just can always take out a +1. A lot of times you may want to either take out a +1 or -1, just depending on how the signs are left with the resulting two terms, if it's either perfectly matching or almost matching. So then we have 3x plus 1 times 2x minus 5. That equals 0. So x here would be -1/3, or x would be +5/2. Really, that step of writing the factors can kind of be simplified. We just switch the sign on the constant term and the linear factor, then divide by the leading coefficient inside the parentheses. Meaning 3x plus 1, if you're looking at that, make the 1 negative and then just put it over 3. Anyhow, let's do one more factoring example just to really drill it home. So if we have 7x squared plus 16x plus 4 equals 0, we have 7 times 4 here, so that gives 28. And everything's positive, so this example is usually pretty quick to figure out. 2 times 14 are going to give us the proper splitting numbers. So we have 7x squared plus 2x plus 14x plus 4 equals 0. And then 7x squared plus 2x, that's all we can do is take out an x. So we're left with 7x plus 2, and the second pair we can only take out a 2, and we're left with 7x plus 2. So our resulting numbers are x plus 2 times 7x plus 2. And that will have solution either x is -2 or x is -2/7. So that is that. All right, so the last thing is the quadratic formula. So if you run into something that doesn't factor, we can always figure out that solutions by applying the quadratic formula. So what does the quadratic formula say? The quadratic formula just gives the general form of the solution in one big complicated looking equation. So what you're generally trying to do is the solution to the equation, so ax squared plus bx plus c equals 0, or the solutions, could be plural, are. So one thing before you start applying quadratic formulas is you want to make sure the way you have whatever's written, you have everything on one side of the equation and 0 on the other side before you start applying this thing. But the solutions are going to be x equals -b plus or minus the square root of b squared minus 4ac, with everything being divided by 2a. So we'll just do one example, but I will make mention of the fact that the thing underneath the square root here, b squared minus 4ac, is called the discriminant, and it determines the nature of the solutions to the equation in question. So the first one, b squared minus 4ac, if it's positive, what's going to happen is the equation will have two real solutions. If it's equal to 0, you have one real solution. And if it's negative, you don't have any real solutions. You'll have, so I'll say 0 real solutions here, but if you are working with complex numbers, you'll have 2 complex numbers as solutions, meaning they're, in this case, their imaginary part is non-zero. So 3b squared minus 4ac less than 0, we have, I'm just going to say 0 real solutions here, but you could say 2 imaginary solutions as well. All right, so I mean, there's nothing really interesting about using the quadratic formula. You just want to make sure that you're evaluating carefully. So example, solve by the quadratic formula. So let's look at x squared minus 10x minus 1 equals 0. So let's just identify what each of the parts are. A is going to be 1 here, B is negative 10, and C is negative 1. So x here is going to be the opposite of the value of B, so the opposite of negative 10, plus or minus the square root of b, which is negative 10 squared, minus 4 times a times c, with everything being divided by 2 times a, which is 1. So let's simplify. We have x equals 10 plus or minus the square root of 104 divided by 2. So basically your 2 solutions, in this case, x could equal 10 minus the square root of 104 over 2, which has an approximate value of negative 0.10, or x could be 10 plus the square root of 104 over 2, which is approximately 10.10. And so that's it. For the most part, that is polynomials in general, and then looking at the specific class of the quadratic polynomial equations, understanding how to graph them, and solving their equations via 3 techniques. So, have a look at the homework and let me know if you have any questions. Otherwise, this is Dr. Lennon signing off.